Hello, I'm going to talk about gravitational waves and collision between black holes. In 1916, Albert Einstein was thinking about waves, and after demonstrating that there were electromagnetic waves, he wasn't sure about the existence of another thing that could be gravitational waves. So that could be waves that attracts that are based on the parameter of mass of an object and that affect the whole universe and that could explain the reason of gravitational attraction. So he wasn't sure about it. He backtracked a bit and wasn't sure. He didn't knew for quite sure, and I'm going to show you how this gravitational waves has been studied in the last 3 years, because gravitational waves are fairly recent discovery. So this is a video that I took from the LIGO laboratory. LIGO is an American interferometer from America, from the United States of America. But okay, I'm going to start the video. So we can see on the background a representation of the space-time continuum, and at the center we have two black holes, and here we have a function that here is fairly sinusoidal. So the two black holes get closer and closer. You can see that black holes have a huge impact on the space-time continuum, the gravitational aspect, because everything near it is densely attracted to it, because blue means no attraction and red means very intense attraction. So here we can notice that the two black holes get closer and closer, and their dense areas in red will start to collide. Okay, so now the simulation slowed down, and here we can see an emergence of some big gap here, because see, this area is higher than the blue one. And this is where shit happen, because black holes will merge into a single entity. Yeah, the movie is frozen here on the original thing. And here I will go backtrack again. So you can see here that the sine wave is colored as the movie plays, and here in the movie is frozen, and here there is a dense modification in the whole gravitational continuum, and then nothing, because the the two black holes merge into a single one, and that's it. Okay, so to detect these waves, the LIGO use an interferometer, um, but I'm going to not detail how LIGO works, but show how a Michelson interferometer works. Um, so I'm not going to go too much in details, but basically there is a laser that emits a ray, and with a semi-transparent mirror, the the wave is either reflected on this side or on this side, so it's semi-transparent, and then after the mirror it comes back here, and from this line it goes back here. There are special cavities to avoid losing energy, and as you can see, the path taken by light to go there, then there is the same length as the path to go there, then there, then there, then there. So then you analyzed it, you compute lots of things, and in 2014 there were this. Um, this is not the first detection of, well, we can say it now, but at the time we weren't sure about what it was. So we have strain. Strain is a unit to define the distortion between in the gravitational field. So basically, you can imagine that you have two piece of metal, and this unit, the strain, measure the infinitely small displacement in of this. Um, Basically, no, I can't explain it like that. But just it measures how much the the gravitational field is distorted. Um, However, we can notice that the frequency here, I'm not going to go in detail with that, but here we have frequency. So with a fast Fourier transform, you can see all the frequencies here, and through time, here we can notice that there is not big stuff happening like we could expect. So it was the first sign that we could detect of a gravitational wave, but we weren't sure because this, as you can see here, the length, the in red it's what's detected, and in black the model, and in fact that isn't quite sure. Like, we can't be sure that it's a gravitational wave. So it's just a small detection of it. Then, like in 2016, I'm sure. Okay, so in 2016, the LIGO observed these things. So they have two senders in Hanford in Washington and in Livingston in Louisiana. Okay, so in the first one, we can notice that here pretty much everything is okay, but we get here some sick oscillations, and then afterwards we get like none, as we can see on the simulation earlier. Here we have this pattern here. Same in Louisiana. We have like nothing going on, and then sick oscillations, and then nothing. Here are the models to study these waves. So basically, it's reconstructed wave function. This is the residual thing due to experiments, but it's not very important. And for frequency, here we have a huge amplitude in the frequency near this area. As you can see here, it's big in yellow, and here we have a huge form, unlike previously, where it was really small, like only this small area and this small area. Here we have a huge amplitude. So as you can see here, the strain here is very high, and that's why it's in a yellow-like color. And this was the first thing we were sure it was a gravitational wave, because this center was the LIGO, and it's fairly sure that it's a gravitational wave. Um, then recently in January 2017, that has been announced in the press in June 2017, we have this signal. Where is it? Have this signal. Same as before, we have a pretty much normal strain. Then it starts oscillating like crazy with increasing frequency until some peak where the black holes merge, and then it starts going normally again. Uh, so yeah, it was the second detection. But as you can see, this process is could be full of imprecision, because this is just normal mirrors, like there isn't much things to do. Um, so what if these things were caused by microseisms, like you move the table and it moves slightly, and that could just be it, or stuff like that, so small perturbations, or just normal gravitation moving the small piece of mirror, and thus moving that strain. In fact, scientists thought of this obviously. So this is called a LIGO suspension with a quadruple pendulum. So basically, it's pretty much impossible for them to make a mistake, because uh, this is the mirror, and there is some really high-tech uh, pendulum thing, so that it isn't impacted by the gravity. And this is so precise that here you can see that the strain is in the unit of strain is adimensional, but it's also 10 to the minus 21, 10 power minus 21, and thus that means that the displacement is really small, obviously, because we humans can't detect a gravitational wave. It's not like it's gonna move our house or something like that. It's really small because we are very far from the the black holes merging. So we have very, very small moves of strain. So I think that's it. If you have questions, you can ask them in commentary. I'll try to answer them. I'm not an expert in gravitational waves, and that's just what I found on the internet. And thanks for watching, and bye.